So today we are going to cover chapters 9 and 10, which is going to be torque, rotational energy, rotational momentum. And basically, these are rehashes of chapters 4, 5, 6, 7, 8, but we're changing our perspective. Instead of thinking about things moving in a straight line, we're going to think about them moving in a circle. So, when we think about pushing things around, right, we usually draw our force diagram arrows as if that force is being applied right to the middle of the object. Because if you do that, all of your force goes into shoving an object to the right. But actually, if you apply the force up here, you're going to shove the object to the right, but there's also going to be this tendency for the entire object to rotate. And we know that in fact real objects do rotate. They spin and yeah. So we're going to take the tools that we built up to talk about forces, and we're going to do our best to use those same tools to talk about what might make an object rotate rather than translate. That's right. We watched it last week in the bullet block experiment. If you apply a force off center to an object, you're going to spin it. Before we get to Newton's second law, let's think about chapter 6, I believe, where we had uniform circular motion. And one of the things that we did in that chapter is we built up a definition of rotational kinematics. So if we have a pi wedge, which is a piece of a circle, in radians, the angle is defined as x over r. If we want the rate of change of that angle, and if we want the rate of change of that angular speed, we can write that down too. Here, x, v, and a are the linear position, displacement, or distance rather, the linear distance, speed, and acceleration, and then alpha, omega, theta are their angular analogs. And this definition let us do things like write our kinematic equations in rotational coordinates. So we could write theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Right? And this is equivalent to the first kinematic equation that we've been using this whole time. And we saw that actually the second and third kinematic equation also had these analogs. What we would like is an analog of Newton's second law for rotational coordinates. So let's start with our definition. Right? F equals ma. Now the acceleration, we've just said, is related to its angular acceleration by a factor of r. So we could take this a this A and replace it with alpha r. So we're making progress. One thing that we know from personal experience, though, right? Why is it not just alpha? Because the r, right, has to come somewhere. So if we want to take, alpha equals a over r, solve for a equals alpha times r. So one thing we know from personal experience is that the further from the axis of rotation you shove something, the more likely you are to get it to spin. So, for example, we opened the discussion with the example of a door, right? So doors rotate on their hinges, and that is how they open. So if we push on a door right next to the hinges, are you likely to successfully open that door? Yeah, that's a negatory. That's not how doors work. In fact, we usually put doorknobs on exactly the opposite side of the door from the hinges. And if you push on the doorknob, then you open the door. We also know, again, from kind of experience, that so say your door is open, right? And there's this thin side of your door that when it's closed, it's against the door jamb, right? If you push, in fact, let me draw this as a diagram here. So here's our door, here's our hinges, here's our doorknob. This is a bird's eye view of a door. So if you push on the door here, that's no good. That's not how doors work. What about if you push on a door like this? Can you open it? Yeah, again, no. Also not how doors work. So we kind of understand that what we need is a force that is both distant from the rotational point and also which is perpendicular to the thing being pushed, right? Being rotated. And we have a kind of multiplication in that okay, can I say that again? Yes. So if we drew a line from the point of rotation to the point where we applied the force, right? We need that line to not be zero length, because if you're pushing on the hinges, the door does not open. We also need the force we're exerting to be perpendicular to that dashed green line there. If it's parallel to that dashed green line, the door doesn't open. If it's perpendicular, it does. There's one more possibility. What if you pushed on a door like this blue line? Is that door going to open if you push on it like that? Yeah, it will, but inefficiently. So now I'm going to make a little room here. The closer you get to the hinge, the more force required. Yep, and if you're pushing on the hinges themselves, then no amount of force is going to move it. All right. So what we need, if we have some arbitrary amount and direction of force being applied on this thing that can rotate, what we need is only the part of that force that's perpendicular. Right? And if we draw the tail of our vector on the, so if we draw first the line from the axis of rotation to where we're applying the force, and then from there we start our force vector, and the angle in this case is going to be the angle between those two things. And we note actually that it's only the sine portion. So like if this is, we're applying a force F, then F sine theta will be the perpendicular part of the force, and that's the part of the force that's going to help us open the door. Now, if you took enough calculus, I mean, you'd have to get to like the third semester of calculus, you would learn about a kind of vector multiplication that does exactly what we want, right? And that would be the cross product of multiplication. We're not going to actually make use of the cross product in this class, but know that this thing that we're doing, it doesn't come from nowhere, right? So our idea here, right, is to, once we've got this F equals M alpha R expression, F sine theta looks like it's for the x-axis. Yes, the way I've drawn this here. F sine theta is for the x-axis because it is opposite the angle that we have defined as theta. And yes, it is also always going to be sine. So our idea here, and I'm just going to briefly appeal to calculus. Since we know force is a vector, acceleration is a vector, right? All these things are vectors. What we are actually doing is taking the cross product of the force and the radius, the r being the distance from the axis of rotation to where you're applying the force. And F cross R will always give you basically the perpendicular bit. And the amount of that will be F R sine theta, always. Where theta is the angle between F and R. And since we've multiplied by R on the left-hand side, we have to multiply by R on the right-hand side. And then we're going to do a little bit of switcheroo here and just write it as m r squared alpha. And this is one of those times where physicists love to just redefine something for convenience, just like the definition of momentum kind of popped out of a manipulation of Newton's second law. Well, here, this thing, mr squared, we call that the moment of inertia. And this is going to be for a point mass. So that this whole thing can be written as, and then this thing here, this FR sine theta, we call that torque. So that now this whole thing can be written as torque equals I alpha. And it looks nice and compact, just like Newton's second law. Okay, questions or comments? Yeah, so you're probably familiar with torque in the context of automobiles. And that is exactly this definition as well. In an engine, whether it's an electric engine or an internal combustion engine, you are making something rotate, like you're spinning something inside the car, right? And whatever method you're using to cause that thing to spin, that's torque that you're applying to make it spin, and that torque gets translated down to the axles of your car to make them spin, and that's what makes your car go forward. So yeah, this use of the word torque, it's exactly what is meant in automotives. Yep, because the more torque you can apply to your drive axle, the faster you can accelerate forward. All right. As long as you have good tires, this is the truth. Okay, so we have a new. It's not really a new tool because this is really just Newton's second law, dressed up fancy. So our perspective, though, in the linear coordinate system that we used in chapters 4 and 5, our perspective was a force is something that causes an object, that tends to cause an object to accelerate in the direction of the force. And here our perspective is a torque is something which causes a tendency to rotate in the direction of the torque. So whether we're talking about linear acceleration or rotational acceleration, it's still acceleration. We're still applying something to it. So those parts are kind of understandable, right? Because our torque is actually made of a force that we're applying to something. But moment of inertia, like how do we interpret that? Right? What's our intuition for what moment of inertia even means? And what I would ask is, what does mass even mean? What is mass? So I see some maybe not so clear explanations of masses. There are some common ones that pop out. Weight mass is just your weight divided by gravity. Like, okay, but that's a little circular since weight is already defined in terms of mass. We say it's a number that corresponds with how much stuff is in an object. I mean, okay, but stuff, I guess that could be technically true, but since stuff is such a vague term, that's maybe not super useful to us here. And we have something that says it relates to the density, but okay, but density is defined as mass per volume, so that doesn't necessarily help. And here, Yusuf has it. What is mass? Mass is a measure of an object's resistance to acceleration. And that's all we can realistically say about mass. Mass is just how much you resist being accelerated. And at this level, at least, we can't say anything more specific about mass. And in fact, you need an awful lot of physics to say anything more specific than that about mass. So moment of inertia, we want to define in exactly the same way. Moment of inertia is just the resistance of a body to being rotated. Right, so not all objects resist rotation with the same degree of vigor. In fact, not all objects of the same mass resist rotation with the same vigor. Which we're going to see here in a moment. When I say body, I mean any physical object that has extent, right? That it's not some mathematical point object. It's actually got volume, a real object. Okay, so our bit of tool that we have here, a torque is caused by a force applied perpendicular to, some books call this a lever arm, which, if you like thinking of this as the lever, that's perfectly all right. So a force applied perpendicularly to a lever causes a change in angular speed. So this is one of those times where I'm going to refer you to my favorite website. And what's my favorite website? Yeah. You guys have it. It's it's Wikipedia. So Wikipedia, of course, has an absolutely exhaustive article on moment of inertia. Just enormous. We don't need all of that detail. What we are going to need from time to time are the actual expressions for the moment of inertia of an object with a particular shape. I'm going to drop that in the chat for everybody. All right. Okay, so when we were manipulating Newton's second law, we actually this moment of inertia object kind of popped out, and we said that the moment of inertia was defined as the mass times the square of the distance from the axis of rotation. This is true for a point, right? So not an actual, not a real three-dimensional object, just a single zero-dimensional point where all of the mass is concentrated in exactly one point. Real objects aren't like that, but we can think of real objects as being made of infinity little tiny points. And if we think of some way to add up all of the infinity little tiny points, then we can get a moment of inertia for the overall object. And of course, the clever way to add an infinity of little points, that's what we refer to as integration. And we're not going to do it in this class, but just realize that's where it comes from. So in a hoop, which is like a circle with all of the mass at a distance r from the center, right? All of the masses at a distance r from the rotational axis, so the moment of inertia of a hoop rotating around the center is just mr squared. If we have a rod, though, we might want to rotate a rod, and this is, of course, a door is also approximately a rod, if you don't think about it too hard. If you rotate this thing around its end, the moment of inertia actually comes out to be 1/3 ml squared, where L is the length of the door, or the rod. If instead you want to rotate this thing about its center, the moment of inertia is 1/12 ml squared. If you have not a hoop, but a solid circle, then you're looking at not mr squared for the moment of inertia. You're looking at 1/2 mr squared. So for simple objects, at least, the moment of inertia will always be like some constant times the mass times some distance squared. And you don't have to memorize these. You do have to be aware that there are different expressions that exist and be able to look them up should you need them. Questions or comments on this page? other expressions beside these? Yeah, if you look at the wiki page, there's disks with holes in them, there's cylinders, there's spheres, there's boxes, there's octahedrons, tetrahedrons. So yeah, both the shape of the object and the axis about which you are rotating it make a difference. 1/2 is at what point again? 1/2 is for a solid disk rotated around its center. Okay. What we've just done here, this is essentially all of the physics for Chapter 9. Use of scalar moments, yes. So we are only going to be worried about scalar moments because in general, the moment of inertia of an object depends not just on shape and axis, but also which direction you're rotating it. So if you have a disk and you are spinning it, if you're spinning it this way, that is the minimum moment of inertia. What if you actually wanted to spin it, you wanted to flip it end over end, right? That's going to be a different moment of inertia. So that's what, so in general, the full moment of inertia, for an arbitrary spin direction is going to be a matrix, actually. But here we're only going to be considering spins around a simple axis in a simple direction. Because, yeah, I mean, if you guys, we're not going to bring in integrals for this class. We're definitely not going to bring in matrix multiplication. That's just asking for trouble.
What's the CMD squared one again?
Oh, this is the general form. So some constant times the mass times some distance squared.
Okay, thank you.
Let's do a couple of problems to illustrate. For the most part, by the way, we will be considering situations in which rotation doesn't actually happen. So it's what's known as static or stability situations, or also equilibrium. So those are some words that we're going to use to describe these situations, right? Either equilibrium or static or stable. If you were an engineer, you would spend an entire semester just studying static situations. And here we're going to spend a week studying static situations. So we're only going to brush the very surface of it. Let's say we have a seesaw. Static equilibrium is just equilibrium, yes. Let's say we have a seesaw, and there are two kids on the seesaw. This question actually came up during office hours, but I think it's a good enough example that we're going to do it again. Now these kids are not sitting on the end of the seesaw because they're not doing the whole up and down thing that seesaws were designed to do. They're just trying to balance. Those are some weird kids. You are not wrong. Hey, everybody has fun in their own way. You know. Yeah, those are R1 and R2. So the R1 and R2 is going to be the distance that these kids are from the center of the seesaw. The center of the seesaw is where the pivot of the seesaw is at. You thought it was a P? You guys are always throwing shade at my handwriting. Alright, is that better? Alright, I'm glad you approve. These kids are exerting forces on the seesaw equal to their own weight. There's also a normal force exerted on the seesaw from the pivot. Alright. So if we have a static or a stable situation, we actually have two conditions. And one of them we already know from chapters 4 and 5. Right? If a thing is not moving and it's not accelerating, then the sum of forces is equal to 0. If it's not if it's static though, it's also not rotating. Or so we're going to have a situation where not only the sum of forces equal to 0, the sum of torques is also 0. And these two things together are what define equilibrium. Okay, so let's start by summing up our forces. Right, the seesaw is not crashing into the ground, nor is it flying off into the sky. And so I almost skipped a step. Up will be the positive y direction for forces. So the sum of forces in the y direction is going to equal the normal force minus m1g minus m2g. And because this is a static situation, we know these have to sum to 0. So the normal force is just the sum of the weights of the two kids. I guess if we were being really pedantic about it, we could also say that the seesaw itself has some mass, and okay, you're right. And because this class has a reputation for pedantry, I'm going to fix that up. So the normal force is enough force to support all of the weights that are in play. That's not really a surprise. Right, that's exactly what we expected, given our experience with chapters 4 and 5. We do have a second condition to examine, though. And when we're looking at torques, we need to be a little careful about how we define our directions. Right? So here, instead of up, down, left, or right, we're looking at clockwise or counterclockwise rotations. The old convention is that if a torque would tend to cause a rotation in the counterclockwise direction, that's a positive torque. So something like that is positive. And if it would tend to cause a rotation in the clockwise direction, that's negative. At this level, it doesn't actually matter which one you choose to be positive or negative. But keep in mind that most people, including me and your textbook, will default to saying that counterclockwise is the positive direction. So the sum of torques, right? If we've got if we've got these forces, then we have some torques, right? We have the orange kid exerting a torque proportional to its weight and to the distance it is from the axis of rotation. We also have a similar torque from the green kid, but the green kid would tend to cause this whole seesaw to rotate clockwise. So he's going to be a negative torque. And then we get to the normal force and the weight of the seesaw. Now, this is like our introductory question where we realize that, hey, you can't actually open a door by pushing on the hinges. And we have the same thing going on here. Both the normal force and the weight of the seesaw are pushing down exactly at the points of rotation on the seesaw, so they're going to produce no torque. Right? Because they're at a distance of 0 from the axis of rotation. Is it negligibly small or no torque at all? It's actually exactly 0. So if the normal force, so if the normal force and the weight are applied exactly at the pivot point, then their torque is exactly 0. Why is it mgr, not mgr squared? That is a good point. So the r squared bit, that goes into defining our moment of inertia. But if we have a torque, right? A torque is just F, right, perpendicular bit times r to the first power. All right, so normal force, weight of the seesaw, produce no torque in this situation, which means we have m1gr1 equals m2gr2. G's are going to cancel out. Get m1r1 equals m2r2. And I think, actually, this is basically the algebra and analysis that is going to apply to an upcoming lab that you will be doing soon. Yep, hold that thought, Yusuf. We're going to get to that after the break.
Dr. Wolf, I just want to confirm what we did. So for the torque, the force, we just plugged in MA, and in this case, A was G, right?
For the torques, that is a good question. So the torques are all a force times a distance, right? So the only forces that we had here were just weights, right? So M1G, that's the weight of the orange kid. And the orange kid was applying his weight to the seesaw at a distance R1 from the center.
Got it. Thank you.
Okay.
I have a quick question. Why are we subtracting the M2GR2? Like, isn't it also going down?
It is, but so here, and this is the key, right? When we are doing a torque analysis, it's not up and down that matter, it's clockwise and counterclockwise. So like if it was just the green kid by himself. I don't know why I'm saying him for the green kid. It's a stick figure. So just the green kid. Their weight. If their weight was the only thing causing the seesaw to rotate, it would tend to rotate that way, which is clockwise. And if it was just the orange kid, they would tend to rotate it the other direction, the counterclockwise direction.
Okay. And then, like, the N and the N3G, they're both zero because, like, they're in the middle, right?
Right. So they won't cause any rotation at all, right? Because they're applied right at the point we're letting the whole system rotate.
Okay, thank you.
Yeah. So I think this is a problem from your textbook, and they have something like, one kid is 20 kilograms, the other one's 30 kilograms. And the distance between them is 3. So I think that's the problem from the book. They said R1 plus R2 is 3, and M1 was 20 kilograms, M2 was 30 kilograms. Yeah, we went over it during office hours. So that'll be on YouTube before too long. So the question was something like, what distance does the smaller kid have to be from the center? Okay. So I'm not going to get into the weeds on doing the algebra bits, because actually looking at your tests, you all are just fine on algebra. Like, plugging in numbers is nobody's problem. So we're going to end this here, and we're going to go on to the next example.
Good question. What are we actually solving for this? Are we solving for, like, the mass of one? Or are we just gonna plug those in and, like, solve for, like, the overall T?
Yeah. So in this problem, and this is from the book. They were asking for R1.
Okay, thank you.
All right, we're gonna do one more example before we break for a leg stretch, and this is one of my favorite problems actually. So we're gonna have a little bit of fun here. We've got some firefighters leaning a ladder against a building, and they're doing a bit of training. They're going up the ladder in all of their gear. Right, so they've got maybe a little backpack thing happening. They've got a hat of some sort. They've got a fire axe. There we go. That's definitely a firefighter and not a park ranger. The quiz was going to be after the break, actually. I'm sorry. there's some forces involved here. The ladder has its own weight. Mass of the ladder. There is the firefighter. There's also actually some friction, right? So there's contact with the ladder and the building, and there's contact with the ladder and the ground. So at the ground, there is some friction. And there is also a normal force. Right? Because anytime you've got contact with the surface, you're going to have a normal force. There is also, right, there is a normal force from the building to the ladder, and there is a friction between the building and the ladder. So what we are interested in here is at what angle right? What's the limiting angle here? The minimum angle that we can put this ladder on and not have the whole thing slip. Right? We want the ladder to be stable for the firefighter to climb all the way up. Because we want it to be stable, we need two things. We need the sum of forces to be 0. We need the sum of torques to be 0. So, let's start with, let's say that, this ladder has been well engineered, so we have a pretty good idea of what the coefficients of friction are. So a coefficient of friction between the ladder and the ground, the rough asphalt, is like 0.8. And coefficient of friction between the building and the ladder is only like 0.6. The mass of the ladder itself is, say, 25 kilograms. The mass of the firefighter with all their gear is, 150 kilograms. And the total length of the ladder is 20 meters. Okay. So we want, even though this is a more complicated problem than the seesaw, we want to approach it in exactly the same way. So what's the first thing we do? Yeah, we sum the forces. We're going to start with Newton's second law for forces. So sum of forces equals 0. Oh, actually, Braden Graham, excellent point. We need to define our coordinates. How about up and to the right? There we go. So for the torques, it will be clockwise and counterclockwise. But for forces, when we're doing just the force analysis, right, it's linear coordinates is what we need. So first we do a force analysis with linear coordinates, and then we do a torque analysis with rotational coordinates.
When we set the force equal to 0, that's because like there's like no acceleration, right?
Right. If
So
there,
the why
oh, sorry, go ahead.
so then I was like confused, like what is like making like the torque equal to 0?
Well, we'll deal with the torques in a minute. But the idea here is that this ladder is not moving and it's not rotating, because if it were, our firefighter would be having a very bad day. Does that make sense?
Yes,
Okay.
thank you.
Yeah.
So it's just because the only thing that's there is the force of gravity, and they're canceling out.
I'm sorry, Logan. I can barely hear you.
So it's zero because the only force is gravity.
Not because the only force is gravity, but because what we desire is a situation in which the ladder is stationary. So we are assuming we've got what we want, a stationary ladder, and we are going to solve for the characteristics that we require in order to make it stationary. Does that make sense?
Is
Right.
it like how do you show that it's a zero force? Like the total force? I guess I don't understand why it's zero still.
It's the same. So remember back in chapter 5, and we did some box on a ramp problems. And we started the problem by just saying, like, hey, the box is not slipping down the ramp. What does the coefficient of friction have to be for the box to not slip down the ramp? Does that make sense? Where here we're saying, hey, the ladder is not moving. What kind of normal force and friction do we require for the ladder to not move?
So that would be zero for force and friction.
Well, the total force is zero. No individual force is zero. But when we add up all of the different forces in the x direction, we'd better get zero. Because if we don't, that means the ladder is slipping to the left. And that's no good.
Okay.
So we've got actually only two forces in the x direction here. We have friction at the ground and normal force at the building. So these are actually going to be equal to each other. The friction at the ground is equal to coefficient of friction times the normal force at the ground. So we can say this is mu 1 n1 equals n2. In the y direction, we've got a few more forces. But we still need them to sum to zero, because if they don't, the ladder is either flying into the air or falling toward the ground. Neither of which is a great situation for our firefighter. So the forces that we've got, in the positive direction, we've got the friction from the building, we've got the normal force from the ground, and in the negative direction, we have the weight of the ladder and the weight of the firefighter. And again, we would like these to sum up to zero.
May I ask a question?
Of course.
Why did we not consider the normal force between the person and the ladder?
That is an excellent question. Uh, that's because our system is the ladder plus firefighter together, right? Um, so yes, there is a normal force from the ladder to the person, just as there's a contact force from the person to the ladder. But Newton's third law, those are going to cancel out because they're internal to our system. Right?
Thank you so much.
Yeah. So the kind of implicit thing here is that our system is both the firefighter and the ladder, at least for our force analysis. Great question. So our friction from the building is going to be mu times the normal force from the building. So we have mu2 n2 plus n1, and we'll move all of the weights to the other side. So we have the sum of masses times g. And at this point, we can use our result from the x direction to substitute in for n2. So let's just say mu2 mu1 n1 plus n1 equals all of this stuff. Factor out an n1. And then finally we solve. So n1 is equal to the total weights on top divided by this weird thing that's a product of coefficients of friction. Everyone with me here? Okay. So the mass of the ladder is 25, mass of the firefighter is 150. Where did the 1 come from? It came from factoring out an n1 from both of these terms. So when we factor out an n1 from the second term, we get a 1. So the numerator up here is, so the total mass is 175, g is 10, so we get 1750 in the numerator. And then in the denominator, we have 0.8 times 0.6, which is 0.48, and then plus 1. So our normal 1 is going to be 1,180 newtons. Of course, that lets us get a value for our n2 as well, since n2 is just n1 times mu1. So times 0.8, and that gets us that n2 is about 945 newtons. And then, of course, if n1 is 1180, then the friction at F1 is equal to 945. And if N2 is 945, then that means that F2 is 570. I'm rounding here. Everyone with me so far? Don't understand that last part about friction. So, right, friction is the coefficient of times the normal force. So once we have the normal force, we could just multiply by mu and get the friction. Is friction 2 going upwards? It sure is. So the ladder is contacting the vertical side of the building, and friction is always going to go along a surface. And here the surface is vertical, so is the friction. Which values, Jess?
Question. What's the general formula for friction again?
General formula for friction is this. Friction is equal to some coefficient times the normal force.
Okay, thanks.
So for N1 and we have an expression here for N1. And once we had this expression, I just plugged in all of these values from the beginning. And these values in brown up here, those are just my best guess, like at what sort of values we'd have.
Good question. Why is the normal force 2 going to the left instead of just going up as well?
Yeah, so
Like other normal forces?
so the normal force from a surface is always going to be perpendicular to the surface, right? Normal means perpendicular. So here, if the surface is vertical, the normal force has to be horizontal.
Because it's leaning against the wall.
Yes.
Okay, thank you.
So yeah, you can imagine if you were leaning against the wall, like you might be leaning to the right against the wall, which means the wall is pushing on you to the left. Okay. You may notice that nowhere in all of this work did theta even appear. So how are we going to solve for theta if we haven't even written down an expression that has theta in it? So it's not quite black magic, but it is a torque analysis. Right? So far, we've only done forces. We have to use our other stability condition. Right? So sum of forces has to be 0, but sum of torques also has to be 0. Just inverse tan y over x. I mean, I can see where you're headed, except the sum of forces in the y direction is 0 and the sum of forces in the x direction is 0. So we're going to get inverse tan of 0 over 0. And actually, I mean, 0 over 0 may or may not be a problem for the inverse tan function, but it's definitely beyond the scope of tools that we usually use in this class. But a torque analysis, that we can do, right? We have solved for N1 and N2 using force analysis, right? We solved for two variables using two equations. forces in the x and y direction. If we want a third variable to be solved for, we need a third equation. And in this case, it's torque, right? We're going to do a torque analysis. And here is the really beautiful thing about torque analysis. If an object is not rotating, then it is not rotating about any axis you choose. The axis of rotation could be anything we want on this ladder, because if it's not rotating at all, it's not rotating around the middle, it's not rotating around the bottom, and it's not rotating around the top. So of those three choices, bottom, middle, top, what would seem to be the most convenient choice for the axis of rotation?
Bottom.
Bottom's a good choice. We have any other votes? Is it just bottom? Just bottom. Okay, I guess we're doing bottom. Why is bottom so convenient?
That's the angle we're trying to calculate.
It is, but all of these forces, like we're to do a torque analysis, we're going to have to calculate the perpendicular bit of all of these forces. So we're going to have to do some breakdowns no matter what. The point of choosing your axis at the bottom is if you choose the point of rotation at the bottom, that means N1 and F1 provide no torque because they are at the axis of rotation. It's like pushing on the hinges. So if you choose your axis at the bottom, N1 and F1, no torque. And we just have to look at the torques of the other forces. If you choose your axis in the middle, then the weight of the ladder produces no torque, and you just have to balance the other 5 forces. And if you choose your point of rotation at the top, that means that all of the forces at the top produce no torque. So you just have to balance the other 3 forces. So since everybody voted bottom, we're going to do bottom. So we're at the bottom. So why is the weight of the ladder in the middle? Because all objects, you can treat the weight of an object as if it is applied at the center of mass of the object. So if our axis of rotation is down here, that means the torque due to N1 and the torque due to F1 are 0. So we have 1, 2, 3, 4 other torques to consider. So the first one is the weight of the ladder. So the weight of the ladder is mlg. The distance between the weight of the ladder's application and our axis of rotation is half the length of the ladder. But how much of this force is perpendicular to the ladder? Why half? Because the weight of the ladder is in the middle. So, and the length of the whole ladder is 20, so the weight is only 10 meters from each end. So, a little bit of cleverness here. Right? If theta is the angle between the ladder and the ground, then this angle up here is actually 90 minus theta, right? Because this is a right angle. Is everyone with me on that angle identification? So the perpendicular part of the force, right? We want to take this force, this mlg, and divide it up, right? We could divide it up into a parallel bit and a perpendicular bit, and it's only the perpendicular bit that we want, so that's going to be sine of 90 minus theta. Okay. The weight of the firefighter is also going to produce a torque. Oh, sorry, one more thing. What direction is the torque produced by the weight of the ladder going to tend to rotate this thing in?
Clockwise.
Clockwise, yep. So it's actually negative. Okay. What about the weight of the firefighter? Clockwise or counterclockwise?
Clockwise.
Yeah, still clockwise. Right, because we're rotating down at the bottom. So any forces that are pointing down are going to tend to go clockwise. So this is also going to be a negative torque. The firefighters like the full length of the ladder away from our axis of rotation, so that's just an L. And the angle breakdown is going to be the same as the weight of the ladder. So that's going to be a sine of 90 minus theta. Next force. Friction. So is F2, is that going to produce a positive torque or a negative torque?
Positive.
Yep, that one's going to be positive. It's a full length of the ladder away from the axis of rotation. And then we just have to worry about the angle, right? So if friction is going up, straight up, then that's going to be partially parallel to the ladder, partially perpendicular to the ladder. And we really want to know what's this angle here, right? So sine of whatever this angle is what we're going to need to tack on here.
Isn't that theta?
Well, if we draw in a horizontal, we know that the angle between the horizontal and the ladder is theta. And the angle between the horizontal and F2 is 90 degrees. So this has got to be 90 minus theta here.
Can I interrupt for a second?
For sure.
I'm trying to understand what we did for the torque. So that is the force times the R, which is the distance.
Yes.
So how did this sine 90 minus theta come from?
Because only the perpendicular part of the force counts.
Of the force. So that's part of the force or part of the...
Yeah, so this is like force times distance times sine of the angle between them.
Got you. Thank you.
So I think that's how your book writes it down. They write torque equals FR sine theta.
Yeah, it does.
Okay.
Thank you.
Okay. One more force. One more force to break down. N2. Is N2 going to be a positive or a negative torque? Yeah, it's going to be a positive torque. It's going to rotate in the counterclockwise direction. It's a full length of the ladder away from the axis of rotation. And then we just have to break down the angle. So the normal force is directly to the left. That's going to be partly perpendicular to the ladder, partly parallel to the ladder. Right angle there. And so this angle here, it's the angle between the ladder and the horizontal, which we know is theta from the definition.
Can you real quick, like, just show where all the torques are at again? Because I'm so disoriented right now. I don't even know which way is which, or
Yeah.
what is what.
So we have 6 forces in this diagram. Because we chose our axis of rotation to be at the bottom, right? So we're like, this ladder's not rotating. So if it's not rotating, then we might as well say it's not rotating about the bottom where it hits the ground. And there are actually 2 forces. 2 of our 6 forces are applied at the point where the ladder hits the ground. So that means those 2 forces produce no torque. It's like pushing on the hinges of a door. Since they don't produce any torque, we then worked our way up the ladder and calculated how much torque each of the other forces would exert. So we started off with the weight of the ladder, and we did a little geometry and figured out that the angle between the weight and the ladder was actually going to be 90 minus theta rather than theta. Same for the weight of the firefighter. And actually, same for F2. And then N2 is the only one where the angle between the ladder and the force is actually theta instead of 90 minus theta. So we have 4 terms in our torque analysis so far, and they correspond to the torque produced by the weight of the ladder, the torque produced by the weight of the firefighter, the torque produced by the friction between the building and the ladder, and the torque produced by the normal force between the building and the ladder. Does that help, Logan? Okay. So I'm going to copy this and give us some room to finish this off. Draw it on your shower wall, then take a picture of that and put it on a shirt. No joke, I have a t-shirt that just says, "You forgot your exam." And I wear that on Halloween sometimes. All right, so we have a little bit of algebra work to do on this whole torque thing. If all of our angles had been inside a sine of 90 minus theta, then it would have been easy. We could have just factored out the sine of 90 minus theta, moved everything else off, and done inverse sine. That'd be great. But we don't have that. We have some of them are sine of 90 minus theta. We have some of them are sine of theta. But isn't sine of 90 minus theta, isn't there another way of writing that? What's another way of writing sine of 90 minus theta? Exactly, that's cosine. And if you don't remember that, that's fine. You don't have to remember it. All you have to remember is that Wikipedia has a list of trig identities. And if you feel like something is, like maybe there's a different way to write a trig thing, go look it up on Wikipedia. But yes, sine of 90 minus theta is the same as cosine theta. So we get 0 equals minus mlg length over 2 cosine theta minus mfgl cosine theta plus f2l cosine theta plus n2l sine theta. And we know how to deal with this now. We've been doing this since kinematics, right? All the cosines go on the left-hand side. All of the sines stay on the right-hand side. And on the left-hand side, I'm going to factor out the cosine theta. So we have cosine theta times mlg length over 2 plus mfg length minus f2 length equals n2l sine theta. And then we're going to divide both sides of the equation by cosine and both sides of the equation by n2l. So this bit is going to get divided off over here, and this bit is going to get divided off over here. And it becomes a tangent. You got it. Now I think it's probably safe to plug in numbers. Do the lengths all cancel out? Yes. Yeah, the first one you see like this will be jumbled. All right, because it's a new kind of analysis. But this is also harder than anything you'll get from the book or on the test. So here's what you should do. right? You should do some of the easier problems from the book, and then by the time my crappy internet has uploaded the lecture videos, you can take another look at this, and it won't seem like Greek. And yeah, if we had picked the top as the axis of rotation, we would have had 3 forces that produced no torque. And this would have been a simpler bit of algebra. So it was the difference between considering 3 torques and 4 torques. But you're going to get the same answer either way. Well, there were 6 forces. But because of where we put our axis of rotation, 2 of them produced a torque of 0. So we just ignored them. I'm glad you enjoyed it, Nathaniel. All right. All of that work just to say that, hey, this, right? Don't let this get any shallower than 48 degrees or your ladder is going to fall. Okay, so I think this is a good opportunity to take a 10-minute break. I have, my clock says 10:11 right now. Let's be back here at 10:21, and we're going to talk about energy and momentum in rotating objects. All right, see you at 10:21. All right. Anyone who's not back from break, raise their hand, please. Recording's going strong. Although I probably should have turned it off during our break and then restarted it, but yes, I said raise your hand if you're not back from break. That is my version of a joke. If we have time at the end, I will tell you my favorite joke of all time. It actually absolutely killed with my 152 class last week. All right. So, chapter 9 was all about extending our idea of forces to things that are rotating, and we ended up with this idea of torque. That was all of chapter 9. For chapter 10, we would like to extend our ideas of energy and momentum in order to deal with systems that are rotating. And that's going to be really straightforward. So recall that we had this definition in radians, mind, right? This definition only works in radians, where the angular speed of an object undergoing circular rotational motion is v over r. Also, in chapter 7, we brought forth the idea of kinetic energy. Kinetic energy is equal to 1/2 mv squared. If we do a straightforward substitution here, turning our v into an omega, that gives us something like 1/2 m omega squared r squared. And, right, we get this m and this r squared. Right, those together make the moment of inertia for a point, as we saw in the last chapter. So there is some motivation then for defining rotational energy equal to 1/2 I omega squared. That's it. That's half of chapter 9 right there. So we are just adding one more kind of energy that we know how to track. Right? We're adding R. We are adding that to our list of energies, including kinetic energy. We're in chapter 10 now, Jasmine. Gravitational potential energy and spring potential energy. Right. So one more kind of energy. It's cool, but it's like not anything we're going to write home about, right? We already had 3. We add a 4th. Okay. The same ideas still still apply too. Like the work energy theorem still applies. Right? So if there's no external forces, there's no change in energy. The other thing that we add in chapter 10 is we generalize our idea of momentum. Right? So momentum we defined as mass times velocity. Well, again, if we use this sort of thing here, we get m omega r. And remember, so that's, if we had one more factor of r in there, is that with angular speed? Yeah, the omega is angular speed. So right now we still have, like, this is still exactly the impulse momentum theorem from chapter 8. If we multiply each side by another r, well, there's that mr squared going on again. And this j times r, so remember that j, our impulse, is a force applied for a time. So if we multiply that by our r again, we're going to have F times r times delta t. But from our last discussion before the break, a force times, the radius, the distance between, a force times a distance to the axis of rotation is a torque. So we end up with torque times the time equals a change in I omega. And this thing, this quantity here, I omega, we typically call that L, capital L for angular momentum. I know, L is already overused. There are too many L's flying around. You are not wrong. So our rotational energy, we just toss in with all our other energies and deal with it the same. Angular momentum is a little fussier because we have to consider it separate. From linear momentum. So now we actually have two statements of conservation of momentum that are true at the same time, right? So change in linear momentum is 0 and change in angular momentum is 0.
I'm sorry to interrupt, but I'm confused. Isn't that just change in the moment of inertia and omega? Where does the L come in?
We call it L. So I times omega, we call that L.
Oh, okay. Thank you.
Yeah, just like when we had our mass times velocity, we called it P. Um, okay, so we have two separate impulse momentum theorems. We have to deal with them separately. So torques cause a change in angular momentum, and forces cause a change in linear momentum. We have other questions or comments on this page? Because we're going to
Yes,
do some examples. I'm sorry?
yes, please. I don't even know where to start. So I just want to back up just from the very start. So that was kinetic energy, which is half mv squared,
Yes.
right? And then we plug that into, oh, okay, so that's the I point, and then we plug things. So that first part is okay. But the second part, I'm kind of confused. I forgot what the J is.
Impulse.
Impulse, that's the one. And impulse is change in the rate of change, right? Of in momentum or something like that.
Almost. Impulse is the thing that causes a change in momentum, right? But impulse is caused by a force applied for a time, and that causes a change in momentum, right? So,
Oh, yeah, I confused it. Power. That's the rate of energy change.
yes, that's
Okay,
right.
got you. And then all we did is just plug in the chapter 6 angular velocity and angular acceleration stuff into the equation.
That's
And then at
exactly
the
right.
end, you said sorry, um, and you said angular momentum is separate from linear momentum. Is that what you mean?
Yes. So they are both
Okay.
conserved, but they are conserved separately. You can never add linear momentum plus angular momentum. You have to do them separate.
Okay, that's the part that I was a little lost about. Okay,
Yeah.
thank you so much. That
But
makes a
you
lot more sense.
yeah, but you can add rotational energy plus other kinds of energy.
Got you. So we can add energies, but we cannot add momentum. And by that, you mean like, for example, when we break down forces, we can add them together. But when it comes to rotation, angular momentum and linear momentum, these cannot be combined at all.
Correct.
Got you. Thank you.
Left side in the orange color, are we kind of just deriving the formulas for change in linear P and change? Yeah, that's right. So starting from what we know from chapter 8, which is the impulse momentum theorem, and I'm not deriving it per se, but I'm providing a plausibility argument. Like it's not a proof, but it's a plausibility argument. Like yeah, you can see why we would define angular momentum the way we do. Does that answer your question, Casey? It is not. What you need to understand is the pink. The the kind of derivations and plausibility arguments, I think of those like clothes hangers, and the stuff you have to memorize is like your clothes, right? It is not strictly necessary to use clothes hangers in order to get dressed in the morning, but it does make it easier. So if you understand like the arguments for why something is, it's easier to like cement in your mind what it is you're supposed to remember. At least um, that's my experience. Jolin, change in angular momentum equals torque times time. Exactly. Change in linear momentum is force times time. Change in angular momentum is torque times time.
This is neither here nor there, but why do we use P for linear momentum?
Uh, Historical reasons. Um, it's because that's the way Newton wrote it down, like 400 years ago, and we've just been kind of following his example. Newton's a crazy guy. The the first half of his life, he produced all this really cool science and mathematics, and then the second half of his life, he spent locked in an attic trying to transmute lead into gold. Um, his biography is just crazy. All right. So here's our definitions of rotational energy and angular momentum. Let's do an example or two to kind of illustrate what we mean. This first one, this problem is going to sound like the setup for a bad joke. We have a ramp. So a hoop, a cylinder, and a sphere, like a solid ball, all go to a ramp and start rolling down the ramp from the same height. Which one reaches the bottom first? So we have a hoop, a cylinder, and a ball. All have the same radius. All have the same mass. Which one of them gets to the bottom of the ramp first? Yeah, Nathaniel, that's exactly the sort of joke setup I was thinking about. A hoop, a cylinder, and a sphere walk into a ramp. Um, so I've got some guesses for cylinder. Any particular reason y'all are picking cylinder, or you just have a you're just betting people? Money's on the ball. Does it depend on volume? It's an interesting question. So the ball only looks like it's a head because I can't draw three-dimensional pictures to save my life. They're actually at the same height at the beginning. I just can't draw perspective.
Couldn't it also depend on the coefficient of friction between the hoop and the ramp, the cylinder and the ramp, and the ball and the ramp?
Excellent question. It's a frictionless ramp. No friction. And they all roll without slipping. So no sliding, only rolling. All right, now I have some people saying same time, same time. Here's what I propose. And see if this sounds reasonable to you. Whichever of these objects is going the fastest when it reaches the bottom, that's the one that hit the bottom first. Does that seem reasonable? So, of the tools that we have learned over the course of this class, or actually more think about the tools that we learned today, what tool seems like the right one to analyze this situation? Right? Kinematics, forces, momentum, energy. What seems right? We've got energies and momentums and inertias out there. So momentum, remember, we need to know, like we use momentum for either collisions or for, we need to know both a force and a time to get a change in momentum. So I think actually we want to start analyzing this using energy. Right? There are no external forces between, say, situation A at the top and situation B at the bottom. No external forces means no change in energy. So let's start with the hoop. Change in energy from A to B is 0, which means energy at A equals energy at B. What kind of energy do we have at situation A? Yeah, just potential energy. This is the height that we're dealing with at situation A. So we're going to have mgh. What energies do we have at situation B? At the bottom, B for bottom of the ramp. We have kinetic, but since they are rolling, right, that means they are rotating. So we also have rotational energy. What is the moment of inertia for a hoop? Okay, see, why is the change from A to B 0? Because there's no external forces like acting on these objects as they go down the ramp. So no external forces means that energy is constant. It can change forms, but it can't leave or enter. Yeah, if there were friction, the change in energy would not be 0. That is correct. Yeah, Yusuf, the moment of inertia for a hoop is mr squared. So we have mgh equals 1/2 mv squared plus 1/2 mr squared omega squared. An m cancels out of everything. And what is this r squared omega squared? How could we rewrite that? Right? What's omega times r? Yeah, omega times r is our linear velocity, so omega squared r squared is v squared. Right? So we have 1/2 v squared plus 1/2 v squared. That's just a whole v squared. So the velocity of the hoop at the bottom of the ramp is square root of gh. All right. Let's do the next shape. The cylinder. A bunch of this stuff is going to be the same. Still has conservation of energy. So we still have energy at the top equals energy at the bottom. And those kinds of energy are still mgh equals 1/2 mv squared plus 1/2 I omega squared. Yusuf has helpfully looked up what the moment of inertia of a cylinder is. Moment of inertia of a cylinder is 1/2 mr squared. So we get mgh equals 1/2 mv squared plus 1/2 mr squared omega squared. M's all cancel out. The r squared omega squared becomes a v squared. So we get 1/2 v squared plus 1/4 v squared. That's 3/4 v squared. So v is equal to the square root of 4/3 gh. Last shape. The sphere. Same setup. Change in energy is 0. Energy at the top equals energy at the bottom. Same kinds of energy. And again, Yusuf was enterprising enough to look up the moment of inertia for a solid ball already. Yeah, we're solving for linear velocity because we figure whichever shape has the highest linear velocity when it reaches the bottom, it must have reached the bottom first. Right, so 1/2 plus 1/5 is 7/10. Okay. Questions or comments? And yeah, 10/7 is slightly bigger than 4/3. So the ball is the fastest of all.
Sorry, this may be a silly question, but where's like the 2/5? Because I don't really see like there's no numbers put on any of these, the hoop, the cylinder, or the ball. So how are we getting different values if they're all starting off with the same formulas?
Yeah, so the moment of inertia for different shapes is different, right? So for a point or for a hoop, it's the mass times the square of the radius. But for a disc or a cylinder, it's only half as much, right? And the ball is even less than that. And that's just because different shapes, like depending on the shape of your object, it may prefer to be like not all shapes resist rotation by the same amount, I guess is what I'm trying to say. Right. And you kind of know this intuitively, because if you've ever like played with a pen and kind of spun it around in your fingers, you know that not every object is as easy to spin in your hand as a pen is. Right? So even if things are the same mass, the shape of the object makes a difference.
Okay.
So Dayton asks, couldn't it be faster but take longer? Well, so we solved for the speed that it was going to be at the bottom, but there's nothing that's stopping us from doing the same analysis for the speed at the halfway point or the quarter point or the eighth point, right? So if the ball is faster at the bottom, it's going to be faster at every distance.
If the radius was different, then the one with the greatest would roll down the quickest, right?
Yeah, so if the radius was different, then we would be considering a whole different thing.
Got you.
Yeah.
Thank you.
So a larger radius means more resistance to rotation.
More resistance, because I thought it would cover more distance quicker.
You would think, but it would also take more energy to get it spinning.
Oh, got you. Thank you.
Yeah. So either a larger radius or a larger mass would both increase the object's resistance to being rotated. So in this case, Yusuf, it actually doesn't matter how massive the objects were, right? Because the mass, it canceled out. So even though at the beginning I said, yeah, all objects have the same mass, that ended up not mattering. So you could have a really heavy object and a really light object. As long as they had the same shape, they would roll down the hill at the same rate. And actually, this is how Galileo did his experiments on falling objects, right? So there's this apocryphal story that Galileo dropped things off the Leaning Tower of Pisa and saw how long they took to hit the ground, like that he had a helper timing that. But that is not the case. That is not what he actually did. That just makes a good story. The reality is he built a ramp and had objects rolling down the ramp. And as long as they were the same shape, they rolled down the ramp at the same rate, no matter how heavy they were.
Can I ask a question?
Mm-hmm.
So, I'm still trying to like grasp chapters 7 and 8, and so I'm just kind of trying to get a feel for like, say I don't have any of these chapters mastered just yet. Well, is it possible to, I don't know, kind of get a hold of all of these things by next Friday, like in your eyes,
It's
knowing that?
totally possible. I would recommend that you budget a large amount of time, though, like maybe on the order of 20 hours between now and then.
and just like try to do as many practice problems as I can. Because honestly, just like the textbook, it's really confusing for me just because I'm not, I don't know, like it's hard for me to really get the concept by just reading something. So you suggest just like trying to watch as many like conceptual videos and stuff as possible to really grasp it and do as many examples. Is that pretty much how you would go
Yeah,
about
so
it?
doing problems is where the best learning happens. And if reading the textbook isn't working for you, that's okay. We live in the future, and there are video explainers on the internet. So I linked in the syllabus. I linked a set of videos by Walter Lewin, who is a retired professor at MIT. He's got some wonderful lectures. He does diagrams and demonstrations. You should definitely look at those. There are other physics explainers on the internet too, Khan Academy, or Crash Course, um, or Organic Chemistry Tutor does a great set of videos on physics too. So yeah. So if one source doesn't work for you, there are definitely others.
Okay, thank you.
So Abigail says, I'm a little confused how the cylinder was the fastest if they're all the same mass. Yeah, it turns out that it doesn't matter what their mass was, right? Just like falling objects all fall with an acceleration of g, no matter what their mass is. Things rolling down a hill, also, it does not matter what their mass is. It does matter what shape they are, but it does not matter what their mass is. Nathaniel, yeah, I forget what the guy's name is, but I've definitely seen some Minecraft physics videos too, which are pretty hilarious. My 10-year-old watches a lot of Minecraft meme videos, and he stumbled upon a set of Minecraft videos that were on physics by mistake. Um, and I hear from the next room, like, forces and displacement, and I come in, I'm like, what are you watching, kid? Um, so they are all the same size, like in their radius. So they all have the same radius, but they are not all the same shape. So, right, so one of them, yeah, so a hoop and a ball, even if they both have the same diameter, we wouldn't say that they're the same shape necessarily, right? It's just the way I drew them, they kind of look like they're the same shape, but that's only because I'm bad at drawing. Okay, cool. You're right, Jillian. I totally forgot to pause and have a quiz today. So I'm just going to make the quiz assignment in Web Campus and give everybody a point for it. That is my bad. Did I grade the quiz from last week? I mean, not grade per se, but basically, if you turned in anything, you got a point. That's how the quizzes go. Um, like, if you turn it in, you get a point. If you didn't turn it in, you didn't get a point. And you didn't I just haven't input the grades yet because I have a test from my other class that I'm in the process of grading, so I'm a little behind. Let's do one more problem before we have to peace out for the day. Yeah, if you emailed it, it's fine. I will still find it. All right, so we've got 3 kids on a merry-go-round. This is a bird's eye view. The originally they are all riding on the edge of the merry-go-round, which has a radius of 1.6 meters. They are all originally at the edge. Right, and these masses are 22, 28, and 33. Also, the mass of the merry-go-round itself. So, wow. Use capital M for the merry-go-round. Is 100. Okay. So originally, this is spinning at a rate of 20 RPMs. And the question is, what if this kid, this 28 kilogram kid, gets up and walks to the center? Now what? Yeah, so the first thing we definitely, RPMs is not a unit we can do math with. We need to convert from RPMs to radians per second. So 20 revolutions per minute. And this is like a chemistry style, dimensional analysis. 2 pi radians is the same as 1 revolution. And 1 minute is the same as 60 seconds. So this is like 2.1 rads per second. Okay. When I'm rounding even more egregiously than I normally do, I think, oh, 2 pi? That's like 6. So 6 over 60 is a tenth. So yeah, 20 revs per minute is 2 rads per second. But I know some people absolutely just die when I say pi is about 3. All right, so there's our speed converted. What we would like to do next then, so here's our idea, right? That a torque applied for a time causes a change in angular momentum. There are no torques in this situation. So no torques means no change in angular momentum. Yep, no torques, no forces, so no change in momentum. When the 28 kilogram kid is at the outside, we will call that situation A. And when they are at the inside, we will call that situation B, when they're at the middle. Since there's no torques, that means that the angular momentum at situation A is equal to the angular momentum at situation B. And in both of these cases, we can write that down as the moment of inertia at situation A, angular speed at situation A, equals moment of inertia at situation B, angular speed at situation B. So what we need to do is we actually need to calculate what the moment of inertia of this whole system is in situation B and situation A. When you've got a system that has multiple parts, like we do here, the moment of inertia of the whole thing is the sum of the moment of inertia of the parts. Yeah, so if our system is composed of, right, object 1 and object 2 and object 3, then the moment of inertia of our whole system is equal to the moment of inertia due to object 1 plus the moment of inertia due to object 2 plus the moment of inertia due to object 3, etc. So if we've got a multi-part system and we want the moment of inertia of everything, that's just the sum of the individual moments of inertia. So the merry-go-round itself is more or less a disk, and the kids, we're going to treat them as points, right? Because their mass is pretty highly concentrated at a particular location. It's not really spread out. So yeah, we're going to treat the kids as points and the merry-go-round as a disk. So the moment of inertia of the merry-go-round, since it's a disk, it's going to be 1/2 times the mass of the merry-go-round times the square of the radius of the merry-go-round. I guess you're right. Disk with a K is like a computer thing, and disk with a C is a shape. Like I said, this whole class is full of pedants, and so you are pedantically correct, and I will change it. So 1.6 is about 1.5, and 1.5 squared is like 2 1/4. So 50 times 2 1/4 is going to be like 125. And then each of the kids are basically points. So the moment of inertia of the first kid is just the mass of the first kid times the square of the radius. So that's 22 times 1.6 squared. For the second kid, it's going to be 28 times 1.6 squared. For the third kid, it'll be 33 times 1.6 squared. I'm actually going to use a calculator for that one. My mental math is running out of juice. All right. So the complete moment of inertia for this system at time A is just going to be the sum of all these pieces. Right, so it's going to be 337. If that 28 kilogram kid moves to the center, then that means that they're now at a distance of 0 from the axis of rotation. So they don't contribute anything to the moment of inertia. So we just leave out this 72 bit. So the moment of inertia after the kid crawls to the middle is only 265. And now we come back to finish this problem off. The angular speed after the kid crawls to the middle is equal to IA omega A over IB. 337 was 125 plus 56 plus 72 plus 84. Yep, sum of all the individual moments. And then IB, the 265, is the sum of all the moments except for the 28 kilogram kid, because the moment due to that kid went to 0 because he crawled to the middle. Okay, so after the kid crawls to the middle, the angular speed of the merry-go-round goes up to 2.65 rads per second. So that kid is not enjoying the merry-go-round as much, but the merry-go-round overall speeds up, so the other two kids are having more fun. The more typical example for this sort of thing is, imagine a figure skater, and they're doing that spin thing with their arms outstretched, and then to speed up their spin, they bring their arms in close. So they reduce their own moment of inertia and speed up their angular velocity in the process. Hey, comments or questions on this last problem?
Dr. Wolfs.
Yes.
Hi. So you said that torque is 0 because there are no forces.
Yeah. There's no
Well,
forces here that would cause a torque.
Well, but there's weight though. Like, shouldn't there be a force then?
So there is weights, but all of the weights here are going like into the page, which means that's the kind of rotation that they would produce, right? And we know that the merry-go-round is not going to flip end over end, right? It's only going to spin around, right?
Yeah.
So you're right. There are technically some forces, right? But they aren't going to cause the rotation that we're looking at.
Okay. Thank you.
Yeah, so it would have been more accurate to say there's no forces that would produce a clockwise or counterclockwise rotation from our current perspective.
Thank you.